Welcome to The Explainer, where we break down some pretty complex topics. And today, we've got a real head-scratcher. How on earth does a giant metal ship float? Let's get right into it.
Think about it. It just seems to defy logic, doesn't it? You have this enormous steel ship weighing hundreds of thousands of tons, just bobbing along on the ocean. But a tiny little pebble sinks right to the bottom. Well, it's not magic. It all comes down to some really elegant physics discovered more than 2,000 years ago.
And to solve this whole puzzle, we've actually got to go way back in time, all the way to ancient Greece, to a legendary mathematician named Archimedes, and yeah, a very famous bathtub. So, let's dive in.
Okay, so the entire secret, the golden rule of why anything floats, from a little rubber duck to a massive supertanker, it all boils down to a constant battle between two incredibly powerful forces.
So on one side, you have gravity. That's the total weight of the ship, all its cargo, everything, constantly trying to pull it down into the water. But fighting back against that pull is an upward force from the water itself, and we call that force buoyancy.
And this right here, this is the core of Archimedes' brilliant discovery. For anything to float, that upward push from buoyancy has to perfectly, exactly, match the downward pull of its weight. It's this perfect, invisible balancing act happening all the time.
And you can see that balance perfectly right here. As the ship's weight pushes down, it shoves water out of the way. It displaces it. It'll keep sinking just far enough until, bam, the weight of the water it has pushed aside is exactly equal to its own weight. At that very moment, the forces are balanced, and it floats.
Okay, so that's the big idea. Simple enough, right? Well, calculating this for a nice simple box is one thing. But as you can probably guess, real ships, they're just a little more complicated.
Let's start simple, though. For a basic box-shaped barge, finding the underwater volume is pretty straightforward. You just multiply its length by its width by its draft. And draft, by the way, is just the technical term for how deep the ship is sitting in the water.
But here's the catch. Real ships aren't perfect boxes, are they? They've got all those curves at the front and back to help them move through the water efficiently. So how in the world do engineers account for that complex, curvy shape?
Well, they solved this with a really clever little tool called the block coefficient, or CB for short. The easiest way to think of it is as a shape factor. It's basically just a percentage that tells you how much of an imaginary box the ship's hull actually fills up.
So a big, full-bodied cargo ship might have a CB of, say, 0.7 or 0.8. All that means is its underwater volume is about 70 to 80% of a perfect box that has the same length, width, and draft. A sleek, fine-lined yacht, on the other hand, would have a much, much lower CB.
All right, so we've got the ship's shape down, but let's add another layer to this whole puzzle. We've talked about the ship, but what happens when the water itself changes? Like when a ship sails from a freshwater river out into the open ocean. Now check this out, because this is really interesting. Salt water is actually denser than freshwater. What does that really mean? It means it's heavier. It packs more mass into every single cubic meter, which means it provides a stronger upward push.
And because that denser salt water pushes up with more force, a ship moving from a river to the ocean doesn't need to sink as deep to displace its own weight. It'll actually rise up a bit. It floats higher in the water.
And the amazing part here is that this isn't just guesswork. Ship officers can predict this change with incredible precision. They use this exact formula to make sure the ship stays stable and safe as it moves between different kinds of water.
Okay, so we've covered all the physics. Now, let's see how these incredible principles get used every single day in the very practical, very high-stakes world of commercial shipping.
Cargo officers, they live by this number called TPC, or tons per centimeter. And it's this beautifully simple idea that tells them exactly how many tons of cargo they need to load to make the ship sink by 1 single centimeter. Super useful.
All right, so let's put it all together and see how these concepts, buoyancy, density, TPC, all come together in the real world. We're going to walk through a classic problem, the kind of thing a ship's officer might have to solve to get their license.
Okay, here's our situation. We've got a box-shaped barge in a freshwater river, sitting at a draft of 2.5 meters. The job is to load 180 tons of cargo and then head out to the salty open ocean. The big question, what will its final draft be?
Okay, first things first. We need to find its starting weight, what we call displacement. So we calculate its underwater volume, that's 60 meters long by 12 meters wide by its 2.5 meter draft.
We multiply that by the density of fresh water, and we get an initial displacement of exactly 1,800 tons.
Next up, let's load that cargo. We figure out its TPC in fresh water is 7.2 tons per centimeter. So, loading 180 tons of stuff will sink it by exactly 25 centimeters. That gives us a new draft in the river of 2.75 meters. Simple.
And finally, for the big move out to sea, we use our density formula. The barge, now heavier, moves into that denser salt water, and it rises up just a little bit, settling at its final draft of 2.68 meters. And there you go. Puzzle solved.
So what's the big takeaway from all this math? Well, every single one of these calculations is really about one thing: maintaining a safe margin. That watertight volume of the ship that's still safely above the waterline, that's known as reserve buoyancy. You can literally think of it as the ship's own life jacket.
So, from a simple principle discovered in a bathtub to the complex calculations that literally keep global trade afloat, the laws of flotation are just a perfect example of physics in action. But that leads to a final, pretty modern question. We know water density changes with temperature and how salty it is. So as global warming alters our oceans, how might these fundamental laws present brand new challenges for the future of shipping? Now that's a puzzle for a new generation to solve.